Hey everyone, welcome to this live session of your daily equation. Looking forward to spending about an hour with you, fielding some of the questions, comments, or thoughts that you have. And again, I say anything you disagree with, you should feel free to push back, and I'll try to look at the comments to see if there's any responses to my responses. So this really can be more of a conversation than, one way you ask the questions and I try to give you the answers. I am not the sage. I know some things. I do not know everything, and I'd love to hear things in which you perhaps have a perspective that differs from my own. All right, I should also quickly say, in these sessions and also in your daily equation, we haven't, I don't focus on the virus. We all know why we're here. We all know what's going on in the world today. But I do hope that you guys are doing all right, and that your family, your extended family, your friends are. I mean, everybody is impacted in one way or another. But I hope that the impact is something that you have been able to deal with, and maybe if your daily equation has helped a little bit with that, well, what could be more gratifying than that? I should say quickly that on occasion when I miss the sessions, it's not because I'm out usually, playing baseball or doing something like that. My mom is in the hospital. She doesn't have the virus, but it is so complicated. Anybody that has a loved one in the hospital right now, you know how difficult it is. You can't visit, you can't go in. The patient, your loved one, feels completely isolated. So I'm dealing with that as I'm trying to do some other things at the same time. So apologies on occasion when I miss a session. Again, I don't know how long we're going to keep going on with your daily equation, but at least it's something that helps me clear my mind once a day as well. All right, let's move on then to the topics of the day. And first question that I see here from Haraprasad Ravakumar. I think I may have actually pronounced that correctly, maybe. Asks, what happened to yesterday's video? And actually, that question is a good one. It's related to what I just actually was mentioning a moment ago. I was rushing so fast to get yesterday's video done that I made a little mistake toward the end of the video. I don't know if you looked at it too carefully. Nothing obviously conceptually was wrong, but one mathematical equation toward the end had one term that shouldn't have been there, and it sort of made me feel like I needed to fix it. So we took the video down. I'm going to fix it, this weekend or something, and we'll repost it with that little change in there. So that's what happened to yesterday's video. Very, very good question. And you see that I'm totally straightforward with you. All right. So what other questions do we have on the more physics front? Let's see. We have Brian, our physical time. So this is from Xinhang Shen says, and this is, I think, one from Twitter, and then I'll go back to the live YouTube in a moment. Our physical time measured with physical clocks is still absolute, i.e. invariant of reference systems, and thus there is no relativistic space-time in nature. Therefore, based on relativity, all what the cosmological theory describes is wrong. So I'm going to interpret that question in the following way, which is, if you have studied relativity, if you've gone through the early episodes of your daily equation where I was focusing more on relativity, you know that one of the main lessons that Einstein taught us with relativity is that there is no preferred reference frame in the universe, in the sense that if you and I are moving relative to each other at constant velocity, no acceleration, so we don't feel any speeding up, I should say speeding up. We don't feel any speeding up, any slowing down, then we have the right to claim that we are at rest, and it's the rest of the world that's rushing by us. And any observer in a frame of reference that has that no acceleration quality associated with it can make that claim that they are the standard of rest against which all motion from their perspective is delineated. Now, that then runs headlong into what seems to be tension with our cosmological theories. And this is what Xin Hang is referring to. Our cosmological theories talk about things like the notion of the amount of time since the Big Bang. We never say the amount of time since the Big Bang on this clock or that physical device that may be moving relative to other clocks. When we speak cosmologically, we say it is 13.8 billion years since the Big Bang period. We describe it as if there is a universal time, as if there is a universal frame of reference with respect to which that time is measured. So what in the world is going on? Relativity taught us that there is no such universal frame of reference. And the answer is that in the universe, our universe, there actually is a special frame of reference. Our universe appears to be homogeneous and isotropic, which means that from an appropriate perspective, if you look out in any direction, the physical qualities you see are pretty much the same. If you measure physical qualities in any large enough volume of space, regardless of where that volume happens to be in the universe, we believe that the physical properties that you'll measure will be the same. That's what we mean by homogeneity and isotropy. But that quality, which is a very, very special physical quality of our universe, is something that only holds true in particular frames of reference. And it's those frames of reference that we have in mind when we speak about the age of the universe or other cosmological properties. So fundamentally, there is no frame of reference that is singled out over all others, but cosmologically, because of the physical environment within which we live, there is a special frame of reference. It doesn't come into the laws of physics in any special way. You can choose any frame that you want to write down the laws of physics, but if you want your observations to be as simple and clean and economical as possible, there is a frame of reference that gives you that economy. And that is a reference frame with respect to which we describe the cosmological features of the universe. So yes, very good question. I appreciate that one. Reed Johnson from the live chat asks, what math classes should physics students take to become string theorists? Question number one that you need to ask yourself is, do you want to be a string theorist? And I don't mean that sort of tongue in cheek. I mean, I'm sort of identified as a string theorist. I do other things. It's not my be all and end all footprint in science or in life. But you need to ask yourself, is the search for the unified theory, is this particular search for unified theory, is putting gravity in quantum mechanics, does that fire you up? And yeah, if that fires you up, then string theory may well be the right direction to go. However, you need to bear in mind, it could be the case that you work on string theory for the next 20, 30, 40 years. You advance the subject, hopefully, along with the other string theorists working around the world. But you may still be in the position that I and other string theorists are in right now, which is we don't know if this theory is right, in the sense that we don't know if it describes our physical universe. I mean, we know when our mathematical equations are consistent. We know when we haven't made a mistake. But we don't know whether our mathematics is describing the world until we have observation and experiment that links the physical qualities of the world with the mathematical symbols that we develop on paper. And so if that prospect frightens you or frustrates you, then again, I would think twice about imagining being a string theorist. Now, putting all that to the side, if you decide to be a string theorist, the math that you need, look, you need all the basic stuff. You cannot jump over the basic things. Mathematically, you have to take differential equations. You have to take all of the math necessary to do the calculations that, for instance, we've done in some of the earlier episodes. Multivariable calculus, complex analysis is a pretty useful class to take as well. And then as you keep on going, you need differential geometry if you are going to focus more on, say, on the extra dimensional qualities of space. You need algebraic geometry if you want to investigate those questions with the most powerful tools that mathematicians have developed. You need topology, algebraic topology, differential topology. And, what I would suggest is take as many of those courses as you can, but ultimately, you should learn the math that you need for the particular research problem at hand. There's no better way to learn math than when you need it to actually solve a research problem as opposed to a homework set, a problem set. Problem sets are artificial. But if you're actually on a research project that needs a body of mathematics, I got to tell you, I've been, as a student, when I was learning, group representation theory, I do remember this. When I was learning group representation theory, that's something else that you need. I needed it for a research problem. And I studied it with a kind of intensity that I never had when I was just studying a subject because it was a course I was taking. So, in the end of the day, take as many courses in math as you can, but ultimately, your depth of understanding will really reach its potential when you need that math to solve research problems themselves. Okay. Um, the rarest one asks from the live chat, why is gravity called a force if it needs mass? Is this not a reaction, not a force? Well, I'm going to give two answers to this question, the rarest. The first one will deal direct with your question. The second, I'm going to go in a direction inspired by your question. So, look, what is the issue? So, forces are things that can exert influence, but they also respond to influence. If you have a magnet, right, the magnet is exerting the magnetic force as part of the electromagnetic force. And my magnet in my left hand responds to the magnet in my right hand if I bring them close to each other. That's still the magnetic force, even though the magnet in my left hand is responding to the magnet in my other hand. So that's what forces do. They exert influence, they respond to the environment, and that affects the influence that they subsequently exert. There's another question, though, that comes to the fore when gravity is the force of interest, which is Einstein teaches us, and you all know this stuff at one level or another. I'm going to take on Einstein's ideas, I think, starting next week. So, we'll talk about gravity and space-time curvature and connections and metrics and all that sort of stuff. But the bottom line lesson is that gravity is nothing but the curvature of space-time. And so some people say you should no longer think about gravity as a force because objects are simply moving along the shortest possible trajectory in the curved space-time environment that other matter in the universe, in the vicinity, creates. And so, can we still think about gravity as a force in the old Newtonian perspective? And my answer to that is you should feel free to use whatever perspective and whatever language gives you insight into a given problem. If I have the challenge of plotting the course of a rocket ship to the moon, I'm not using general relativity and warping and curving of space time. I'm going to use the simpler description that Isaac Newton gave us, which is, F equals G m1 m2 over r squared, gravity as a force. Other problems, if I'm looking at orbits in the vicinity of a black hole, I'm going to use the general relativistic description, and which I'll have geodesics in a curved space-time environment. And I'll then be using the geometrical as opposed to the force-like language. Bottom line is use whatever language is relevant to the kind of problem that you have at hand. And thinking about gravity as a force, even post Einstein, is still a perfectly acceptable and reasonable thing to do. Manikesh Ranjan asks, are you religious? Well, not in a conventional sense. We've taken this up here and there in these sessions, but I'm happy to address it and maybe say something different or flesh out what I've said before. I was born into a particular religion. I'm culturally a member of that religious tradition. I'm culturally Jewish. I do not follow the religious rituals. I do not adhere to the prescriptions of this particular religious perspective on the world. However, I've said before, and many people react negatively when I say this, but I speak freely here. I hope you don't mind. I do consider myself to be a spiritual person in the sense that I am deeply interested in how I and how others try to make sense within the confines of our own conscious awareness of why we're here and what we're meant to be doing with our time, or if we can manufacture some reason for doing things with our time, or if we can gain a deeper sense of what it means to be a human being on planet Earth in the 21st century, which is a very confusing, very rich, but very confusing, anxiety provoking, exciting, thrilling. I mean, it is something that all of us need to cope and deal with and leverage and make use of in order that we feel that we have a full life. And to me, just understanding the external world, which is my professional preoccupation, physics, what are we meant to do? Make predictions about how that star is going to move, or make predictions for why the electron has the mass that it does, or why it has the magnetic properties that it does. All that's the external world, and it's a beautiful focus for us to have within our sights to answer these questions of objective reality, but that's not the full thing. And again, I know that some of you are familiar. I have a book that came out a couple months ago, and it's called Until the End of Time. And I blend in there explorations of the external world through the lens of a physicist, trying to understand the origins of the universe and the origin of stars and planets and galaxies and life and consciousness. But I also then turn the lens inward to try to understand why we humans do what we do as we try to cope with the world around us, why we tell stories, why we invent myths, why we develop religions, why we have creative expression. So that book can give you a much fuller exploration of these ideas than I can do in this brief moment of time. And I'll also note, for those of you, the one of you maybe who's on, I'm actually going to teach a summer course at Columbia University on that book, on these very questions. So if that is interesting to you, for 6 weeks, we'll get together, 4 hours a week and talk about these things. It won't be open to the general public, but if you want to sign up for that course at Columbia, I would love to have you in that class. All right, so that's my thoughts on that question. Let's keep on going. Salman Suleiman asks, hello from Edinburgh. I hope I said that well. I've had practice, but you probably be like, oh, God, what a mispronunciation. Home of the Higgs. Can you please explain the Higgs boson for us? Yes, I'd be happy to do that. So there was a big puzzle that Peter Higgs and others too were struggling with in the 1960s, which is, how do fundamental particles like electrons, the ones that we talk about today, or electrons and quarks and neutrinos, where do they get their mass from? And you might say, well, that's kind of a strange question. They sort of just have their mass. But the reason this question was so pivotal back then, and still today, frankly, is that when we write down the mathematical equations that describe these particles, those equations are highly symmetric, which means that those equations don't change their mathematical form under particular rearrangements of the mathematical ingredients that make up the equations. And in order for them to have that symmetry, which turns out to be vital for the calculations that we do to make sense, for those equations to have that symmetry, the particles need to be massless. And so there was this tension back in the 60s between the mathematical description, which seemed to be doing a fantastic job at encapsulating the patterns evident in particle colliders and accelerators, but those very same successful looking equations were suggesting that the particles, the fundamental particles, shouldn't have any mass at all. They shouldn't, in essence, offer any resistance were you to push on them. So Peter Higgs and others came along and came up with a solution. And the solution is stunning. It's a solution that people resisted, but the solution is, imagine that space itself is filled with an invisible substance called the Higgs field now, but you can think of it as a cosmic molasses. It's not a bad image to have in mind, not perfect by any means. But the idea is that particles fundamentally are massless, but when they encounter the molasses exerts a drag force that if you're pushing on the particle, you've got to overcome to get the particle to speed up. And overcoming the Higgs molasses, this cosmic force, is the origin of the masses of particles. So that's the new idea that Higgs came up with. How do you test this idea? Well, if you take two particles like two protons and you slam them together at high enough speed, bear in mind that they are immersed in the cosmic molasses. So when they collide, they can shake the molasses. And when they shake the molasses, they can have a little speck of the molasses, a little drop, if you will, kind of gets flicked off. And that little drop of the cosmic molasses, that little drop of the Higgs field, is what we call the Higgs particle or the Higgs boson. And so that's the particle that was found at the Large Hadron Collider back in July 4th of, I don't know, 2012 or something. I get the years mixed up by now, confirming this idea that Peter Higgs and others as well put forward some 50 years earlier. That's the idea of the Higgs particle. Okay, so what do we have here? Uh, uh, oh, I had a good question and it ran away. Sir, can we interpret the concept of, so this is Prayodash. Sir, can we interpret the concept of quantum entanglement to the emotional feelings that you have for your mom? Well, that's a touching question, and let me just take it out of the personal, if you will. There have been many, there have been many people who, over the years, have tried to usurp, take over the ideas of quantum mechanics, and use them to explain or even predict weird phenomenon on macroscopic scales, like remote sensing. These people who claim that they can see things that are happening far away, or people that claim that there's some kind of extrasensory perception that links their mind with other minds. And as far as I can tell, all of that is utter nonsense. As far as science seems to indicate, there's no basis for remote sensing. There's no basis for extrasensory perception, at least as it's commonly described. And quantum mechanics certainly is not the answer to that at all. And quantum entanglement is not the answer. Quantum entanglement is a provocative but very delicate link between particles that allows them to correlate their behaviors over arbitrarily large distances. We often describe it in terms of two particles because that's when the linkage, if you will, is strongest. When we have 3, 4, 5 particles, you can still have entanglement, but it gets so diluted among the large collection of particles that the weird properties of quantum entanglement, do something here, affect something over there, they themselves get so diluted that they, in essence, disappear. So when you're talking about something with this many particles, like a human brain, 10 to the 27 particles, the notion of this whole collection being entangled with a whole nother collection is just beyond the bounds of anything that makes sense with our understanding of physics or quantum mechanics. So thanks for the question, but I don't think it is the answer at all. Okay, Kowalajit asks, how does nature know to give every electron the same mass? And your question is framed somewhat anthropomorphically, as if nature has some kind of knowledge base and nature has some kind of particular ability to influence the world, and nature sits there and says, oh, electron, you've got 511,000 electron volts as your mass, that electron same mass, and so on. We don't, I mean, I understand that language, and you're probably just talking poetically. Of course, that's not how the universe works. The universe has these fundamental mathematical laws, as far as we can tell, or at least we develop these laws to describe with greatest precision as we can the properties of the external world. And quantum field theory is our best understanding of the properties and the behaviors of particles. And according to quantum field theory, there is, in essence, an electron field throughout the universe. And when that electron field gets a little bit excited with a certain kind of blip, a certain kind of energetic excitation of that field, that manifests as an electron particle. And the mathematical equations that describe that have a parameter in them. That parameter, in essence, is the mass of the electron. We measure the electron, get that number, stick it into our mathematical equations. But once it's in our mathematical equations, it's one single number that will apply to any and all of these particular excitations of the electron field. So it's not so much that nature has to know to give each electron the same mass. Our understanding is, if quantum field theory is the right description of the world, that the excitations, the lowest possible excitation of this field is what we mean by an electron, And the mass of that excitation is determined by one number in the mathematical formalism. And that one number, because it's not many numbers, that one number is why there is a uniformity in the mass of every electron. Now, not everybody is completely satisfied with that answer. And I should say, Richard Feynman had an idea. I'm pretty sure it's Richard Feynman. He had an idea a long time ago as to why every electron has the same mass. Imagine it goes like this, he said. What if the universe, say, early on, had the shape like a donut, not in terms of its spatial part, but the temporal part? Imagine that sort of as an electron moves, it can kind of circle around through time. So here it is at one moment in time. It circles around and it comes back to that moment in time. But now there'll be two electrons there. The original is still there, and now the new one has joined it because it's done this circumnavigation around the expanse of time. And imagine this electron goes over and over and over again around the temporal loop. Then you'll have many electrons, but all of them are fundamentally the same electron, just at different moments of time, having circled around this circular temporal quality of the world. So according to this kind of crazy sounding idea, the answer to your question as to why every electron has the same mass, every electron has the same mass because every electron would be the same electron. I don't really know if you can make full sense of this idea, but it certainly is a provocative way of addressing the question. But the more traditional answer that I gave using quantum field theory is the one that I would really hope you take away from this discussion. Okay, what do we have here? So I have to answer a question from Ludwig von Beethoven, one of the diehards of your daily equation. So one of your questions is right here. Okay, Ludwig von Beethoven asks, to what extent is it valuable to try and study at a prestigious university abroad, even if they basically teach you the same thing? Yeah, it's obviously not a technical question, but it certainly is a good question of life, if you will, because many of you who are watching this from other countries and want to be, say, a physicist, you face that question. Do you go to school in your own country? Do you go abroad? Do you go to the United States? Do you go to England? Do you go to some of the other centers where certain kinds of science has been the center of attention for a number of decades? And in the end of the day, you can succeed regardless of where you go to school. In the end, the beauty of the field of physics is you're judged on your papers. You are not judged on where you went. You're not judged on who your advisor was. You're judged on the quality of your research papers. And regardless of where you're from, you can write great papers. Now, having said that, there are some who would say what I just said was a little bit naive, and it's slightly naive in the following sense. If you want to get a job teaching, for instance, in country X, and I'm going to take X to be the United States just because I'm here and I'm familiar with it. If you want to get a job teaching in the United States, it is useful to build up a network of people that know you in the United States. And that can be achieved more easily for many people by being in the United States, by being a student in the United States, by being a postdoctoral fellow in the United States. So from that perspective, it can aid you in going forward. But Ludwig, you're completely right. When it comes to learning the subject, if you have good teachers, regardless of where they are, regardless of whether it's a prestigious place or not, if you have a good teacher and you work hard, of course you can make great strides. And of course you can be successful. So it's ultimately a personal choice, but in the end of the day, if you're just focusing upon can you learn the subject really well, yeah, you can learn the subject really well anywhere at all. All right. Caitlin from North Carolina asks, good Bell's Theorem lecture. Thank you, Caitlin. I appreciate that. But I don't understand why the ratio is greater than 5/9. Definitely proves Einstein's hypothesis of locality. I'd actually say it disproves Einstein's hypothesis of locality. So here's how it goes, Caitlin. And for those of you who didn't watch the Bell's Theorem discussion of a few days ago, check it out. I think you'll enjoy it. So, as you know, Caitlin, Einstein was very disturbed by the spooky action at a distance. He was disturbed by the seemingly non-local qualities of quantum mechanics. Do something here and it affects something over here. That non-locality was, like, to him, reprehensible. So he's trying to come up with his colleagues with an explanation that would not need this kind of non-locality. And so, in an effort to get rid of non-locality, he imagined that the widely separated particles always have whatever property is revealed by measurement. So it's not as though a measurement causes one to snap to attention and causes the other distant one to snap to attention. That would be spooky. He says, if this is the result of your measurement, then this particle was always up and this one was always down. So he says quantum mechanics describes the world as if particles can be in a fuzzy mixture of here and there or up and down. But that, he says, is a failure of quantum mechanics, not some true feature of reality. And many people said, well, that's an interesting idea, Einstein, but how would you ever prove it? And the little example I gave in the discussion in that episode was, were I to tell you that my hair is pink, except when you're looking, how would you ever prove or disprove it? Because in order to access the color of my hair, you've got to look at me, you've got to observe me, but I'm telling you, when you observe me, you change the outcome. So it seems to be one of those statements that are untestable. Until 1964, John Bell comes up with an experiment. And as I described in the episode, if you involve these more refined detectors that have 3 settings, and you imagine that these particles don't just have definite features along one axis, but along 3 possible axes, then what I did in the episode was I showed if the idea that the particles have definite features and there's no non-locality, because you don't need non-locality if you have these definite features. If they do have definite features, John Bell's analysis shows there is an experimental prediction that assumption makes. And as I showed you, the experimental prediction is that if you do a whole bunch of measurements of the particle spins among all sorts of random axes, more than 5/9 of the time, they should be pointing in opposite directions. So again, the logic is, if Einstein is right, and if there are these definite features, and therefore there is no action at a distance, no spookiness, then the data had better show that they look like this or like this more than 5/9 of the time. The data does not show that. The data shows that they're like this and like this 50% of the time. 5/9 is 55%. So the data rules out the prediction that comes from Einstein's vision that particles have definite features and you don't need this kind of non-locality. So when the data contradicted the prediction that emerges from Einstein's idea, you realize that there's something wrong with Einstein's idea. Einstein's idea, again, is there isn't any non-locality. You only have definite features. Therefore, what's wrong? The assumption that there is no non-locality. Therefore, there is non-locality. What you do here affects something over there. That's the argument. I also gave some caveats as to potential loopholes. I won't go through them here. But Caitlin, that's the answer to your question as to why the ratio being greater than 5/9, which is contradicting the experiments, disproves the vision that Einstein was trying to put forward. Okay, what do we have here? All right, Pat D asks, can you explain more how quantum phenomenon would apply to macroscopic objects like people and why that is not observable? Yeah, again, quantum mechanics does apply to macroscopic objects. It applies to me, it applies to you, it applies to Swiss cheese, it applies to everything, because everything is made up of particles which themselves are governed by quantum mechanics. So if you have little ingredients that are governed by quantum mechanics, as you put more and more of them together, you're still governed by quantum mechanics. But what we also understand well, and in one of the videos where I described how you go from quantum to classical mechanics. In one of the earlier episodes, I described this in a little mathematical detail, but one thing that we understand quite well is when you have a lot of stuff, a lot of particles, a lot of mass, it's not that quantum mechanics is no longer relevant. It's that the most startling qualities of quantum mechanics get highly suppressed. So, what are the startling qualities of quantum mechanics? They are, if you're measuring the position of a particle, at one moment you could find it here, and next moment you could find it there, and so forth. And the next moment you might find it in principle near the moon. That's weird, right? Particles jumping around. They don't seem to follow the nice kind of smooth Newtonian trajectories that Professor Isaac taught us about back in the late 1600s. Particles can also tunnel through barriers. I haven't spoken about them. Maybe I should. Maybe I should do a little thing on quantum tunneling. Yeah, I think I may do that, right? So, particles can encounter a barrier that the classical physics says the particle can't penetrate. But when you do the experiment, every so often the particle does penetrate the barrier. Weird. But we never see people walking through barriers and it reappearing on the other side, not because it can't happen. It can happen in principle, but for a whole huge collection of particles, each of which is unlikely to pass through a barrier, for them all to pass through the barrier, the odds are enormously against that happening. So if the odds are small for a single particle, they become spectacularly small for a whole large collection of particles. And that's why for macroscopic beings, quantum mechanics still applies, but you don't see the deeply weird features in the macro world because they're suppressed. Not that they're not there, not that they can't happen. It's just that they happen far less frequently. And by far less, I mean spectacularly less often. That is the issue. Okay, what do we got here? Goran Kohler says it's not live anymore. Yeah, it's live. I just answered. Is it not live anymore? So yes, I'm completely here and live in the flesh as far as I know. Okay. Vesemir says, would you say your new book falls more into the field of philosophy rather than physics? And I understand the question, Vesemir. My own view is that there's a somewhat artificial division between physics and philosophy, between science and, frankly, other subjects in the world. So, yes, according to those arbitrary, artificial divisions, what I discuss in Until the End of Time is sort of in the borderland between physics and philosophy. But I don't really consider the way I deal with these issues in the book to benefit from thinking about the sideload nature of the academic world as generally found in university settings. The questions that I take up in the book are honest, powerful, deep questions of physics, entropy, second law of thermodynamics, the arrow of time. But I show how those questions in physics can give us insight into questions that we don't always talk about in physics, like issues of free will or issues of consciousness or issues of trying to make sense of the world beyond just making predictions for this or that quality to emerge from this or that experiment. So yes, I would say it does branch between physics and philosophy, but I would encourage you not to look at that divide as something fundamental. It's what we have erected in order to organize our understanding of the kinds of educations that students can get at universities. But that's not really a good way, I think, of fielding the kinds of insights and knowledge that we humans have developed. Thinking of it more holistically, I frankly find much more interesting and useful. Okay, so C Cat from Cat Family says, is it possible for you to go faster than the speed of light? Would you go back in time? And um, as far as we know, it is not possible for a material object to speed up to and then exceed the speed of light. Roughly speaking, as I described in the episode on relativistic mass, as a body that has intrinsic heft, rest mass, if it is accelerated to faster and faster speed, its relativistic mass gets more and more, which means you have to exert an ever powerful push to make it go faster still. And as that body approaches the speed of light, its relativistic mass soars to infinity, which means you need an infinite push to get that body to speed up to and to reach and then to exceed the speed of light. And since there's no such thing as an infinite force, material objects can't cross the speed of light barrier. That does leave open the possibility, though, that there might be an entity that was born traveling faster than the speed of light, always travels faster than the speed of light, never travels less than the speed of light. So that material object, often called the tachyon, would always be on the other side of the speed of light barrier, and it would never cross. Just as we can't cross to greater than the speed of light, it would never cross to traveling less than the speed of light. As a tachyon loses energy, therefore, it can't slow down, right? It would go slower than the speed of light. As a tachyon loses energy, it speeds up. Everything's kind of reversed on the other side. Now, your question, Kat, had to do with what this would imply for the nature of time. And yeah, there is some weird temporal implications. If I had a tachyon gun, right, and I fired it at you, then according to some observers moving by us in the appropriate manner, they would describe the sequence of events not as my pulling the trigger, the tachyon traveling from the gun and hitting you. They would say the tachyon hit you before I pulled the trigger. The temporal order of what we would think of causal events can become upended if there are these particles that travel faster than the speed of light. So most of us think that it's not possible to travel faster than the speed of light, but it's just to say that no one has completely ruled out, although most people do not believe in this possibility of these tachyons. Okay, what else do we have here? Hi from Turkey. So Baris Gezgen from Turkey. If we consider Lorentz contraction, don't go away. Lorentz contraction and time dilation, is it possible to say a photon would experience the whole universe in an instant at a point? And Baris, I would say poetically, you can say that. And what do I mean by poetically? Well, in your question, you talk about photon experience, and you do put quotes around experience because you and I and everyone else know well that photons don't experience things, right? They don't have conscious awareness. You might think that's secondary to the question, but it's actually important to the question because when I say poetic, I mean that in some sense, a photon would experience all moments at once because our famous gamma factor, 1 over the square root of 1 minus v squared over c squared, that goes to infinity when v goes to c, and v is c for a photon. So there's this infinite time dilation factor, infinite Lorentz contraction factor, so things seem to be infinitely compressed and time to be infinitely slowed down. But the problem is, if you then want to interpret that as an experience, that's where you run into trouble. Photons don't experience things, and therefore the very notion of what it's like to be a photon is putting a conscious being in a frame of reference that a conscious being will never attain, because conscious beings, as far as we know, require material structure, and material structure cannot travel at the speed of light. So yes is the answer to your question, sort of, but the quotes around the word experience that you wrote down, they're actually quite essential to not over interpreting what this means. Take it with a grain of salt that a photon would experience all space at one moment in time. Okay, so what else do we have here? Abhinav 111 asks, what do you think about controlled psychedelic experiences? What do they tell us about our mind, its connectivity with the universe, and so on? Well, I don't know, Abhinav. If you're really interested, you could listen to a podcast I did a couple months ago with Joe Rogan. You know Joe Rogan, kind of cool guy. Enjoyed that interview a lot. I think it was number I can't remember the number, but anyway, you can find it. Joe Rogan and I had a conversation, and I spoke a little bit about psychedelic experiences there. I don't want to spend a lot of time on it here, beyond saying that the mind is a complex and rich and refined organization of particulate matter, which allows it to do spectacular things. And among the things that are quite stunning about the mind is if you introduce just a few distinct chemicals from what the mind usually has coursing through its structure, the experience, the subjective experience can be radically different. What does that teach us? Well, some people say it doesn't teach us anything at all. To me, at least, helps me gain an intuition for the fact that particles can think and particles can feel if they're arranged in the right way. And if you shift the arrangement a little bit, they think and they feel differently. And to have an experience like that, to me at least, gives a more visceral understanding of how it is that the mind's experiences are dictated by the particles that are moving through the brain. Change the particles a little bit, and the experience changes dramatically. And I'm not advocating anybody to undertake these kinds of experiences that can be dangerous. But in answer to your question, that is my own personal view. And again, feel free to look at the Joe Rogan podcast if you want to have a little further discussion of that. Tim Harnick from Belgium. Do you think math is invented or discovered? I actually addressed that a little bit in the very first episode of your daily equation, which now seems like it was years ago, but I guess it was just about a month ago or something like that. So you can see a more complete discussion there, but very briefly, I've had both of those views throughout my life. There are times when I've thought math is out there and all we do is discover it. I've had periods when I think that math is something that we human beings invent to encapsulate the patterns that we encounter in our excursions into the world around us. If you were to ask me what's my perspective right now, it's the latter. I've for a number of years seemed to settle down on this view. It's almost as though, as I said, I think in that episode, when the mathematical research is going really well, it sometimes does feel that all you're doing is chipping away the obscuring layers and the math is there for the taking. And perhaps when the math isn't going as well, you don't feel that way. But this is not a view that's born out of going through sort of difficult mathematical times. I really have come to the view that there are many languages that we human beings invent in order to be able to live more fully in the world and live more effectively in the world. Of course, we invent natural languages that allow us to communicate so we can coordinate our action so that we can better survive. Not always. But we also invent the language of mathematics that gives us a very precise way of articulating certain kinds of patterns in the world, rising and setting of the sun, or the falling of objects, or water as it's going down a stream. And so my view for a while has been it's simply the case that math is one more language, very particular, very precise language, but just one more language that we humans invent in order to fully articulate the patterns that we encounter in the world around us. Okay, how are we doing on time? Oh, time flies. I wonder if I should see if there's anything over on the other feed here. I'll stick to the live one. It's right in front of me. Um, Rob Vandenberg asked, do Q&A sessions like this inspire you? They do. I can't say that they actually literally inspire the next research project, but engaging with you guys and thinkers and folks who just want to know about the world, to me, is an exciting thing. You know, it's exciting that people want to know about things. You know, you can get the impression looking out at certain things that happen in the world and come to the conclusion that people don't want to think deeply. People don't want to explore. People don't trust science. People are not interested in the insights that can come out of this kind of close experiment observation and mathematical theorizing. and to have a group of individuals that come together for these hour-long sessions and clearly have all sorts of interesting and exciting questions that they want to know the answer to. Yes, it does inspire me in that way. Absolutely, for sure. Okay, so what do we have here? So TH asks, as an infinitely expanding universe's energy density goes to zero, does that mean its total energy will decrease as T goes to infinity? Energy, when it comes to the entire universe, is a fairly subtle idea. In fact, the whole idea of energy conservation is one that you have to be very careful about, depending upon the precise shape of the universe. As you're noting, if space goes on infinitely far, let's just say it's flat, and if there's a certain amount of energy density in each volume of space, then the total energy would be infinite. So, what exactly does it mean even to have a conservation law associated with a number that's infinite? So rather than talking about total energy, which is somewhat hard to talk about generally in cosmology, we tend to focus on a region of space. And we ask ourselves, is the case that the energy in that region changes only because there's some energy flowing out or some energy coming in? And that kind of local notion of energy conservation is right there in Einstein's equations of the general theory of relativity. The one thing I would say that's a little bit subtle is gravitational energy is a quantity that you recall from Newtonian physics is negative, right? The potential energy is minus gm over r, right? And that's negative, and it goes to zero when masses are infinitely far away from each other, but it has this negative value as you bring a mass in from infinity. So in some sense, gravity provides an infinite energy well that other things in the universe can mine in order to have positive energy at the expense of ever more negative gravitational energy. And that we think may be the answer to how, for instance, during inflationary expansion, which I've not discussed in these episodes, but in an inflationary expansion, the energy density actually stays the same as space expands. Density stays the same as space expands, so there's more energy, it seems. Where does that energy come from? One explanation is that it comes from the negative energy that the gravitational field acquires. And so it's sort of a trade-off, negative gravitational energy against the positive energy filling space from the inflationary expansion. Van Ron asks, when will your recent talk with Alan Alda be online? I believe that Alan is going to turn that into a podcast in his own podcast, which I think is called Clear and Vivid. So if wherever you get podcasts, wherever you get your podcasts, if you look up Alan Alda's Clear and Vivid, I believe it should be coming out. Or you know what I'll also do? Follow me on Twitter if you don't already, at @bgreene, and I will definitely post that conversation with Alan when it becomes public. It was a really good conversation. We focused on some pretty thorny issues, many of which that I discuss in my book Until the End of Time, and I think you will absolutely enjoy that. Okay. Archer says, is it possible for Dr. Greene to answer all questions at once, especially mine? Well, if it wasn't for the fact that the universe had something called time, everything would be happening all at once. But it does have time, and we have a limited amount left. So because of that, I will not try to answer all questions at the same moment. Sanyukta asks, can you explain Hawking radiation? Let me look at the clock. Yeah, I can explain it. So there are many ways of explaining it in non-mathematical terms. None of them obviously are perfect. And Night Razor asks about my muddy water as I'm talking. And so here's the way to talk about Hawking radiation that I think is quite reasonable. If you have a black hole, right? And in fact, I have a black hole sort of in front of me, right? I can bring see, this is my microphone right here. So this is kind of like a black hole right here, the surface of this here. So right at the edge of a black hole, you have the traditional property of quantum mechanics that particles pop into and out of existence. This is the quantum fulminations that happen in any region of space, regardless of where that space might be. Something special happens when particles and antiparticles pop into existence near the edge of a black hole. Over here, if they're far away from a black hole, particle and antiparticle pop into existence, they find each other, they annihilate, you go from the vacuum to this particle pair back to the vacuum. Near the edge of a black hole, however, when an antiparticle and a particle appear, sometimes one of those particles falls into the black hole. That means the other doesn't have a partner with which to annihilate. What does it do? It just streams away from the black hole. So in essence, at the edge of the black hole, particle and antiparticle appear, one can fall in, the other races away. Now that can happen at every single point along the edge of the black hole, and therefore you have particles streaming away from the event horizon of the black hole. Those particles streaming away constitute the radiation that Stephen Hawking was the first person to recognize back in 1974. And this is believed to be a very general feature that happens in any theory that blends quantum mechanics and the general theory of relativity. So we think that quantum mechanics and general relativity are both part of the physical world, and therefore we think that Hawking radiation is a quality of black holes. All right, time for a couple more. What do we got here? So campus cryptid, I guess in response to that answer, so we finally have our conversation going. Campus cryptid says, what? The universe creates particles from nothing? What? I hope that was the right inflection, Campus cryptid. And yeah, that's one of the weird qualities of quantum mechanics. When you take into account the quantum mechanical uncertainty principle, which tells you in the example that I did in one of these episodes that you can't nail down the position and the speed of a particle simultaneously. Well, if you think about it, speed is associated to energy, and therefore it's telling you that energy can be uncertain. And when you're a little bit more precise about this, you learn that it's a trade-off between the amount of energy and the time which it takes you to measure that amount of energy. It's an E and T trade-off, just like the usual position and momentum one is a P and X trade-off. And so if the energy itself can be uncertain over short time scales, the shorter the time scale, the bigger the uncertainty in the energy. And that means over very short time scales, the energy can actually blossom up. And that energy that just sort of appears, even in empty space, can manifest itself in the form of particles. Now, those particles can't live long, is the usual way that we say this. All this can be made somewhat more precise. So this loose language is obviously loose. But when the particle and antiparticle pair appear, they're living on borrowed energy, if you will. So they can't live on that borrowed energy for a very long period of time because you have the delta T, delta E uncertainty principle. So pretty quickly, the particle and the antiparticle find each other, annihilate, and they give back the energy they borrowed in their own creation. So those kind of processes, excuse me, those kind of processes are happening all the time. They're happening right now, right in front of my eyes. It's just that the time scales are so short and the energies are such that they particles quickly annihilate that on average, you don't see any of that happening at all. You can measure these processes. They have a measurable impact on certain particle properties that we can measure with great precision. So we have no doubt that these kind of properties of the quantum vacuum are correct. And when the quantum vacuum is near the edge of a black hole, in answer to the previous question that inspired your response, the weirdness is that one member of the particle pair can fall into the black hole, leaving the partner to race off into outer space. And that's the Hawking radiation. All right, well, I think we're sort of done, but let me see if I can, I'll finish up with Dang Joss's question. Could there be multiple dimensions of time like there are for space? And I probably should have stopped while I was ahead. Man, I'm starting to have trouble talking. But is it possible? Yes, it is possible. But I should emphasize that having many dimensions of space is something that we know how to cope with, right? We live in a world that has at least three dimensions of space: left, right, back, forth, up, down. So, when a theory, for instance, like string theory, comes along and requires more dimensions of space than that, it's not really a big conceptual, well, it is a big conceptual. It's not an insanely big conceptual leap because we're already familiar with having a plurality of spatial dimensions, three. So to go to four is like just adding one more. It's definitely a leap, but it's not as big a leap as it would be to go from one dimension of space to two. Going from a singular to a plural, that's a big leap. For time, we're familiar with one time dimension. So to go from one time dimension to two time dimensions, that is a big leap. How do you make sense of the second time dimension? Are there two notions of time that exist in conjunction with or in parallel with each other? Is one aligned with psychological time? Is the other somehow a different temporal quality of the world? So these are the notions that you have to struggle with when you want to make a theory that involves multiple time dimensions. But people have tried, and there's been some degree of success. Friend of mine who I've not seen in a very long time, Itzhak Bars, wrote a number of papers, maybe it's a decade or two ago, exploring two time dimension theories. And he, as far as I recall, was able to go pretty far in making sense of those theories. I don't think that anybody takes them seriously. There's no evidence for a second time dimension, but it's at least interesting to see that you can make mathematical sense of a theory that has more than one dimension of time. All right, speaking of time, well, what the hell? I'll just keep going a little bit. That kind of gave me a little boost of energy. So if there's something here that catches my eye before I sign off, someone hit me with like, the kind of question that I just could not possibly resist. All right, Abanov asks me this question. What do you think about the creation of consciousness in the paper of Consciousness and Microtubules of Roger Penrose and Stuart Hameroff? What do I think about that? Honest truth is, I've not read the paper that carefully. I have looked at the paper. I've not read it extremely carefully. And I'd say that, I find it interesting that there are these processes that take place in the brain, that um, there may be some suggestion that there's something to do between them and conscious awareness. But the bottom line is there's nothing that I've ever seen in the Penrose Hameroff ideas which addresses the really deep question of consciousness, which is how is it possible that any kind of physical process acting out on physical particles, whether it's microtubules, quantum entanglement, any of it, how can any of those processes yield the sensation of inner awareness? I mean, if you've never thought about this deeply, after we finish today, you should just sort of sit down and ponder this. Particles, electrons, quarks, neutrinos, protons, neutrons, electrons, they don't have, we don't think, although some would disagree, they seemingly don't have any kind of conscious self-awareness. So how is it that by putting two of them together, or three of them together, or 20 of them together, or 10 to the 27 of them together, how do you somehow yield this property that seems completely disjoint from the qualities of the particles themselves? How is it that you and I have inner films, inner voices, inner lights that are on right now? Where in the world does that come from? And nothing, even if Penrose and Hameroff are correct in terms of the role of these processes and the microtubules, I don't think that it addresses this question at all. And from that point of view, therefore, it's interesting to think about, but I don't think it gives us the insight that we are searching for. So Kusha, an answer to that says, how about a higher level of biological experience? And yes, look, it is the case that there can be so-called emergent phenomena, emergent properties, right? Some people would say, hey, you know, water has this quality called wetness, but H2O molecules, they don't seem to have this quality called wetness. What would it mean for a single H2O molecule to be wet? It's like just a thing, two H's and an O in a particular shape. There's no wetness there. So the folks taking this line of thought would say wetness is an emergent property when you have a lot of H2O molecules. Similarly, conscious awareness is an emergent property when you have a lot of particles arranged in the right pattern. And to some extent, I have to say, I believe that. I still find it deeply puzzling. I do, however, agree with the viewpoint that there's nothing more necessary to have conscious awareness beyond particles and physical laws. So I am in that camp. At the same time, I still find it mysterious that we can have these inner sensations. And I suspect at some point, maybe the first artificially intelligent being that really has conscious self awareness. How would we know that? I don't know. But if there really is a being that has conscious self awareness and convinces us that it has emotions and feelings and it's just a box with chips wired up in the right way, I think at that point, the mystery of consciousness would slowly dissipate. And we'd be like, yeah, consciousness, yeah, it's like wetness of water. It's just the kind of thing that happens when particles are arranged in the right way. All right, someone just asked me if I was going to explain string theory someday. And I'm happy to explain string theory. It's a funny series, this series, Your Daily Equation, because I like the idea that we're talking a little bit of math in each of the episodes because I'm used to either doing my math in my research papers that go to esoteric journals, or when I talk to a general audience, I'm talking totally without mathematics. The famous dictum of Stephen Hawking, every equation in a book cuts down the readership by a factor of two, right? So there's a sense that you don't put equations into the discussions you have with the general public. So I like that this one is a little bit different. At the same time, it does sort of constrain the types of things that I speak about. I mean, if I was going to try to explain string theory and actually include some of the mathematics, it gets kind of involved pretty quickly. So, maybe I'll do a string theory episode and just at the very end throw at you a few of the equations, the string theory, so that I keep in line with my own directive to have a little bit of math in these things. But that's what makes it a little bit hard to jump right in to certain subjects where the mathematics becomes so involved so quickly. Azem Naeem asks, have you met Ashok Sen? I have met Ashok Sen, one of the great Indian physicists, one of the great string theorists, a brilliant individual. And if you happen to know him, do tell him I said hello and hope that he is doing well. All right, Jung Jing Lee says, what is the significance or the status of string theory when there doesn't seem to be any experiment that can confirm or verify the ideas? And yeah, very quickly, you're right, Jung Young Lee. Sorry, I'm trying. Young Lee. The big problem with string theory is exactly the one that you're talking about. We've been working at the theory since the late 1960s. We've made incredible strides that are well beyond what I would have thought we would have been able to achieve by the year 2020. If you ask me as a graduate student in the 1980s, will we be able to have a potentially non-perturbative formulation of string theory? I said, I don't think so. If you were to ask me, will we gain insight into nature of space and time, the fundamental ingredients perhaps that make up space and time, will we have anything to say about that question by 2020? I would say, I don't think so. And yet we have gotten to those places. The flip side, though, which is what the question is about, if you ask me in the 1980s, will we have experimental observations, experimental data that we can link up to string theory by the year 2020? I'd be like, yeah, I think so. Yeah, I would have said, I think we'll find the supersymmetric particles that string theory requires. It's called super string theory. The super is supersymmetry. We haven't found those particles. I would have hoped that we would have find even evidence for extra dimensions in the last couple of decades, the possibility that we'd find missing energy signatures at the Large Hadron Collider to give evidence for more than three dimensions of space. But none of this has yet turned out to bear fruit. So it's not that string theory has somehow failed, which is what some people say. It's just that linking it up to experiment and observation has proven even more challenging than many of us thought decades ago. So, what's the current status? The theory is alive and well and being developed by many people around the world. The mathematical insights are significant. The techniques that have emerged from string theory for dealing with a whole variety of different fields, some in condensed matter theory, some in issues of black hole physics. I mean, there have been a lot of fantastically deep developments, but your question is right. We do not have the observational evidence or the experimental data to show that this theory is a theory of our world. One hopes that that will change, but one also doesn't have a crystal ball to determine the timescales necessary for that to happen. My one footnote to that question is you'd look at any other quantum mechanical theory of gravity, loop quantum gravity, dynamical triangulations, whatever, they face the same problem. When you put gravity and quantum mechanics together, you are exploring nature in extreme realms of very short distances and very high energy. Those realms are very difficult to access experimentally. That's what the problem is. It's not a string theory problem, it is a problem of quantum gravity. Amanda asks, as a science educator, what do you think is the main technique that brings out the most interest, curiosity, and joy of learning from students? Well, yeah, it's a very good question. And I guess I'd quickly say that I can answer in the negative first. I know what does not bring out the interest, curiosity, and joy, and that's the kind of education which is highly assessment focused when the kids are learning in order to avoid getting a bad grade on an exam, when the way that you get a good grade on an exam is by just quickly memorizing a whole variety of qualities, whether it's this or that formula or this or that part of the cell or this or that chemical reaction. You spit it back on the exam, you do well, you leave it behind, and on you go. And science was just this thing that you had to get through. And the sad truth is, for many students, but not all, because there are some great science teachers around the world, but for many students, that, they tell me, is their experience. So I am not soft on the details of science. Kids need to learn the details. Science can't just be some poetic subject, but you need the poetry to go along with teaching the details. You need kids to recognize that with these details, they can learn about the origin of the universe and the nature of black holes and weird qualities of space and time. I mean, when you can have a parallel focus on the very things that make us professionals excited about a subject, if you can get that across to kids, then learning the details is something that has a purpose to it, as opposed to the purpose being getting a good grade on the assessment, which I find tragic when it goes in that direction. And I'm speaking from a personal perspective. I see this with my kids. You know, my kids just want, for the most part, to get through it. And it's very sad to me. And I do my best to inspire them. On occasion, I succeed. And when that happens, it's gratifying. But for the most part, their education is about assessment. To say this student's getting an A, this student's getting an A plus, this one's getting a B. And I'm like, oh my God, are you kidding me? That's not what education should be about. And I don't have the answer. I know that for education, then we need to assess in order that the colleges need to know which students they want to take so they can assess them again. And why do they assess them? Because in the job market, we want to know which students should get the better. I mean, on and on it goes. Isn't there another way? There has to be another way. And frankly, for the health of the world, there better be another way. Okay, so I don't know. People still hanging out. I'll keep it going for a little bit if you guys don't mind. I'll keep answering a few questions. All right. What do we have? Leslie Turner says professional people are boring. Yeah, I'm not going to touch that one exactly. Some are, I guess. Oh, Amanda wrote back. Good conversation. Thank you. I agree. I'll try and implement another way on my own students as well. Amanda, that would be great. Every step matters. Every person matters. And as I said, I don't know the answer. Kids have to take, standardized tests. They have to be able to have learned the material necessary. So it's this tension between the way the world is set up and the way you can imagine the world could possibly be. Pradeep Kumar, is gravity fundamental or is it emergent? Is it an emergent force? And I don't know the answer, but it is a profoundly interesting question, Pradeep. In the last few years, a number of scientists, this actually goes even further back, Ted Jacobson, Verlinde, and so on, have wondered about whether it might be the case that gravity is actually not one of the fundamental forces of the world. Gravity might emerge from properties of space and time when properly understood. In that sense, the charge of a fundamental theory would not be to explain gravity per se, is to explain the deeper structure out of which gravity emerges. That can sound really abstract. Let me just give you one little example, which I think is useful to bear in mind. You and I, we all know what temperature means, right? We know what it means to be hot or to be cold. But there's a deeper explanation at the level of particles. Something's hot when the molecules are moving really quickly, right? When I burn my mouth on my muddy Earl Grey tea water, it's because the molecules are moving so quickly they bang into my tongue and my mouth and they sear it. When it's cold, the molecules are moving slowly. So temperature is an emergent idea that emerges from this more fundamental description of the velocity of particles. It might be the case that gravity is like that. Gravity might emerge from the more fundamental description of the ingredients of reality, and therefore it is not itself a fundamental idea. Rather, it is simply a consequence of the particles behaving in the manner dictated by the deep equations that we are still trying to find. So Saurabh asks, do you think that we may be able to test quantum superposition principle someday? And my answer to you, Saurabh, is yes, we do test it. If you go back to the episode that I had, I forget which one it was, but I did the double slit experiment. Maybe it was in the de Broglie wavelength episode early on. And in that example, the traditional and famous double slit experiment of quantum mechanics, you've got two openings, and therefore your probability wave in the quantum description is going through both of those openings, and it's superposing. The wave from each opening is superposing with the wave from the other. And that superposition is what dictates the interference pattern, bright, dark, bright, dark, bright, dark on the detector screen. And we test that. We do the experiment and we get that interference pattern. We get the result of the superposition of the probability waves emerging from each opening. So I would say yes is the answer for sure. And indeed, it has already happened, and it happens, in fact, all the time. Okay, what else do we have here? Muscle Builder says, how can it seem that the universe and reality is smooth and continuous if in reality it ticks with the Planck time and it's sort of pixelated on the Planck length? And Muscle Builder, I should tell you first, it could be that space and time are smooth. We don't know. But you are right in saying that our deep descriptions are pointing toward the possibility that space and time are not smooth, that space and time may themselves be quantized. They may themselves be made up of ingredients that themselves do not look smooth and continuous, but rather are chunked out on very small scales. So your question is a good one. How could the universe appear smooth and continuous if fundamentally it's not? And you know the answer to that question, actually, because right now you're looking at me on a screen. If you were to look really closely at that screen, you would see the little pixels. But as you move away from the screen, it all looks smooth and continuous, at least if you have a good monitor. Like my monitor is a reasonably good one right here. It looks perfectly smooth and continuous, and yet I know that it's just made up of little pixels. So it's just to say that on the scales that we have access to with today's technology and tomorrow's technology too, we can't probe the Planck length. We can't probe the Planck time. Planck length, as I did in the Planck length episode, that's about 10 to the minus 33 centimeters. We can't probe, even with the Large Hadron Collider, smaller than whatever, 10 to the minus, 18 centimeters, 10 to the minus 20 centimeters, something like that. It's many orders of magnitude too coarse to see if there is a pixelated nature to space. Similarly for time, we can't probe down to 10 to the minus 43, 10 to the minus 44 seconds. It's just too small. Our probing of the universe is so coarse by comparison that the world can look smooth, both in space and time, even though it may not actually be smooth at all. So that's the way the world can fool us into thinking that there are qualities out there when deep down those qualities are not part of the fundamental description of reality. So what else do we have here? Christopher asks, what is the difference between M theory and string theory? In some sense, there is no difference. String theory was the name that we gave to this purported unified theory developed between 1968 and 1995, let's say, because it was clear from the mathematical description that the fundamental ingredient was a little filament of energy that could be with open ends or in a loop, and it looked like a little piece of string. So we called it string theory. Something happened in 1995 that kind of blew all of our minds. Ed Witten, you've probably heard of him. He is the Einstein of our age. He's at the Institute for Advanced Study, which is where Einstein himself was. Ed Witten gave a lecture at University of Southern California that was completely unexpected. And in that lecture, we began to learn that string theory has other ingredients that are not string-like, that can be membrane-like of various dimensions. Membrane starts with an M for M theory. That is one of the possible interpretations of the M and M theory. And therefore, we learn that string theory is really part of a larger theoretical edifice that includes these other entities, not just vibrating filaments, also vibrating flying carpets or vibrating globules and so forth. And so M theory is in some sense the more refined description of string theory. So they're all one and the same, even though they emerged in some sense at different times, and therefore the names are somewhat different because of that. All right, so what else do we have here? Any other questions that people have? Yes, it's rolling by. Let me just try to stop it. Ali asks, do you see any universal time, or would you like to define time tied to biological time? Sure. And I don't see any notion of universal time fundamentally written to laws of physics. But as I mentioned earlier, in the relevant frame of reference that allows our description of cosmology to be as simple as possible, making use of the symmetry of the universe, then there is a cosmic time. It's the time that we quote when we talk about the universe being 13.8 billion years old. But that's not fundamental. That's just an environmental fact. And so it's a quality of time in this environment that we call the universe, but I wouldn't say that it's written in to the fundamental laws of physics itself. All right, another one from Sarab asks, how did life evolve from non-living matter? Answer, I have no idea. I have no idea. You know, that is, a deep question. My guess, and I believe it's the guess that most people would now put forward, is that life is not like turning on a light bulb. It's not as though you have no life, you turn on the switch and you have life. There's rather a continuum between what we would typically call inanimate non-living matter to living matter. And that continuum is along an axis, if you will, of ever greater biological organization or complexity of some sort. So when you have molecules arranged in rather coarse configurations, you can get things like cell membranes. You can get some of the possibility of molecules being able to replicate themselves and so forth, but you wouldn't call it a living system yet. But as this collection of molecules is acted upon by natural selection works even before life emerges. Natural selection is just the capacity of particles that have learned to replicate, those that replicate faster, more efficiently, more stably. They're going to draw in more of the raw material of the environment and thereby dominate the molecular demographics. And as they mutate, they can make even better molecules at reproducing. And some of those molecules will find themselves inside a fatty lipid membrane, and they find that they're able to carry out their processes even better. And over time, the refinement that happens just gives us a continuum from non-living molecules to what we would call living configurations of molecules. That I think is the best answer. So I don't think that we're ever going to come to a point where we say, and there's the final ingredient that gives us life. That's vitalism. That's an idea that was put forward a long time ago that nobody really takes seriously any longer. I think most people believe that particles and laws is all that you need in order for life to have a chance of emerging. You do not need some other ingredient beyond that. Okay, what time is it? 4:28. Maybe I'll do 2 more minutes, just call this a 90-minute session. Well, you tell me when you want me to wrap it up, you folks out there who are asking the questions, because I'm happy to go a little bit longer today. All right. Daniel asks, how do positrons move backward in time as proposed in a Feynman diagram? And look, this is a really good question. I mean, Feynman had creative and unusual ways of interpreting physical law, and one of the ones that really strikes the imagination is he said, look, you can think of an electron as a particle that travels in the ordinary direction of time going forward. A positron is antiparticle. In the diagrams that he wrote down and in the equations that those diagrams represent, he said you can think about that positron as if it's a particle traveling backward in time. I consider that to be an interesting and useful mnemonic, if you will, for writing down Feynman diagrams. I certainly don't think about positrons as traveling backward in time. Yeah, I understand the mathematical equation. I see it up there in the exponent, e to the minus IET versus e to the IET, so I totally get it. And I totally get the diagrammatic representation of these things. But I think in the end, it makes the interpretation of the quantum mechanics seem more mysterious than it really is. You can really think about particles as traveling forward in time, even though Feynman did give us this creative way of thinking about it. I don't find it particularly useful, especially in these kinds of conversations, because then you get into the issue of, well, if there's time travel in the microscopic, why isn't there time travel to the past in the macroscopic? And I think all of that's a red herring, just coming from a kind of misuse of the idea that Feynman was putting forward. Okay, so Corey O'Connell asks, when physicists say our knowledge of physics break down at the singularity of a black hole, what precisely breaks down? Thank you so much. Even there's a little picture there. Thank you, Corey, a tornado picture. And the answer is this, Corey. So we make use of Einstein's general theory of relativity in order to understand the nature of space and time in the vicinity of a black hole. And I'm going to talk about that mathematics, I believe, next week. It comes from a refinement, or really, I should say, an application of Einstein's equations by Carl Schwarzschild back in 1917. That's where the notion of a black hole emerges in Einstein's theory. And here's what you find when you look at the equation. So I'll write this equation down next week. You find that if you try to apply that equation right at the center of a black hole, at the coordinate value r equals 0, you find that the curvature of space-time blows up. It goes to infinity. In fact, the curvature goes like 1 divided by r to the 6th power. And as you know, if you have 1 divided by 0, you put that into a calculator, it says error. Similarly, if you put 1 divided by r to the 6th and you set r equal to 0, you get 1 divided by 0 to the 6th, which is 1 divided by 0, you get error. That's what we mean by a singularity. The mathematics blows up in our face. It goes to infinity. It's something that we have difficulty making sense of. So most of us interpret that singularity to mean that we need a more refined mathematical description of what happens in that region of space-time. Indeed, Einstein's equations do not take into account quantum mechanics at all. So the hope is that if you put quantum mechanics and general relativity together, then we won't have a singularity when we apply that combined mathematics near the center of a black hole. And that's the hope. It's been partly realized in other examples. We're still not quite sure about what happens at the center of a black hole, but that's what we mean by a singularity. I should say, just as an addendum to that, sometimes people use the word singularity as this mysterious word. I know Ray Kurzweil likes to use it that way. The singularity is near. I think that was a point when computer power was meant to outstrip the power of the human brain and so forth. But singularity to a physicist really means one and only one thing. It means we don't know what the hell is going on. When we see a singularity, it means the math has broken down. The math doesn't make any sense. The equations are nonsensical, like 1 divided by 0. And at that point, we say we need better mathematics. So that's, Corey, the answer to what we mean by the singularity in a black hole. Okay. Anything left? Are we done? Oh, any new results, Kevin asks, from LIGO since 2015? Oh, yes, Kevin. Maybe they haven't made the headlines as much. But Kevin, you're noting that in 2015, we received the first gravitational wave signal, 2 colliding black holes. That was a spectacular moment, confirming an idea that emerges from Einstein's theory that had been kicking around for 100 years. And we finally captured one of these ripples in the fabric of space-time. But since then, there have been many other gravitational waves that LIGO has detected. Collisions between neutron stars is a notable example that has given us new insight into how certain kinds of elements are synthesized. And I don't know, I think it could be well over 50 events now have been detected by the LIGO Gravitational Wave Observatory. So yes, it's alive and well and making progress. So it's a very exciting field of physics research. Sanyukta asks, do you think that the Big Bang was an accident? It's hard for me to interpret what that means. Whose accident would it be? Could it be that, some advanced civilization was playing around with their universe creating equipment and accidentally produced this universe? I guess. But now we sort of venture into the land of silliness, right? It's hard for us to make sense of what that would really mean. I don't really ascribe any overarching intelligence to the cosmos. Doesn't mean that there can't be. We discussed that earlier, but I don't find any need for it. And therefore, the whole notion of what an accident would be in the absence of a guiding intelligence leaves me with a sense of, I don't know what I'm talking about. So I hope that gives you some sense to why I have not much to say on that at all. Andrea says 50, 3 exclamation points. Wow, I had no idea, referring to the LIGO detections. Yeah, and that's why you come to these live Q&As, Andreas, to be wowed. No, I think many of you are familiar with that, but I'm happy to fill you in on what's been happening in the last few months or last few years. Subarg TV asks, wait, don't run away. Let me scroll you back. What do you think could be the next big discovery in science? Well, look, I'm extremely excited about the gravitational wave observations that we just mentioned. I'm extremely excited about work that's happening in other fields. There's so much wonderful research on the brain and consciousness and memory And if I was starting out again as a young man with dark black hair, I think I would be tempted to go into the area of neuroscience, or even computational neuroscience, really trying to model the processes in the brain using our detailed insights into machines and machine learning. I think artificial intelligence and general artificial intelligence, I think it's just such an exciting kind of endeavor that's going on. So all of that's great. If you ask me in my own field, what I think the next big discovery will be, or what will spark the next big revolution, I think it is when we finally gain insight into the true nature of space-time. Is space-time emergent? We spoke about emergent gravity earlier. Space-time and its curvature, that's what gravity is. So we're talking about emergent space-time as well. If we could really understand the molecules or the atoms of space and time, then yeah, I think that could easily spark the next revolution. Arpit asks, is the universe infinite? Answer, I don't know. Nobody does. One possibility is that space does go on forever, and that's all there is to it. Bear in mind that if space is infinite today, it would have been infinite near the Big Bang. As you wind the cosmic film further and further back in time, infinity, if you go to half infinity, winding halfway back, well, it's not exactly linear in that way for all, but you get the idea. Half of infinity is still infinity. A quarter of infinity is still infinity. So when we talk about the Big Bang as being this little tiny speck in an infinite universe, that's kind of the wrong image. The Big Bang would have happened on an infinite expanse. Everything that we know in our observable universe, which is a finite distance from us, would have emerged from a little speck on that infinite expanse. But the totality of reality would not have been this little tiny dot that we always picture with the Big Bang. The totality of reality in the infinite version would have been infinitely big, even at the Big Bang itself. Do we know that that's the extent of space? We don't. It could be finite, in which case the little speck image would be a fine image, because if something's finite and you wind the film back, it gets smaller and smaller. And when finite things get smaller, they truly get smaller. Infinite things, when they get smaller, don't. So that's the difference between the two. What else? Inflation. I saw an inflation question. Could inflation, so this is Mr. S, but inflation could be at separate spaces at infinite space. That's exactly right, Mr. S. So you could imagine that there are infinitely many Big Bangs even. Our Big Bang could be one of that grand collection, and it is the eruption of this region of space, but there could be eruptions that happen at different and far flung locations within this wider cosmological landscape. So yes, it could be that the picture of the grandest view of the cosmos is completely different from the one that we entertain when we think about our single universe. That could be a small part of an astoundingly much larger reality if the Big Bang that we know to have yielded our universe yielded universe upon universe upon universe far out on the cosmic expanse. Okay, let's see. SI Monster asks, hey, Professor, a simple question. What are you working on at the moment? Are you working on a theory or are you busy with the World Science Festival? Well, look, I do split my time between research and bringing projects of various sorts out to the public. On the physics front, I've been working for a while on trying to understand these ideas of a multiverse. If we can identify a notion of probability on the multiverse to say which universes would be likely or not, if we can develop a notion of stability on the multiverse to figure out what universes would hang around for a long time and those universes that would quickly disintegrate. That led me into some work having to do with mining quantum entanglement from the vacuum, which is something I worked on with one of my students in recent times. And I also have an interest on trying to explain the dark energy with quantum mechanical processes, perhaps with Casimir energy. So I have a variety of research projects of that sort, but you're right. The World Science Festival was meant to go live in New York at the end of May. Obviously, we're not going to do that, but we are developing programs that, number one, we are distributing now. This actually is sort of one of them, but more straightforward and more familiar World Science Festival offerings where we have a variety of scientists and conversation about cutting edge ideas. We are going to start releasing those new programs sometime probably in June and throughout the summer. So that is another thing that I'm involved with. But if you're asking, I'll tell you a few other cool things that I'm doing. I have this piece that I did with the composer Philip Glass about a boy going to the edge of a black hole. It's a symphonic piece. It's a stage with an orchestra and a film and a narrator. It's called Icarus at the Edge of Time. I'm working on a sequel to that right now, so that's kind of fun. I'm also working on a live stage show on quantum mechanics. We had a live stage show, you may know, on the general theory of relativity called Light Falls. It was on PBS last May. You're not supposed to be able to see it unless you pay for it, but you go to, you search for it online and someone has a bootleg copy up, and take a look. Love to hear your comments. So that's a version of the kind of presentation I'm talking about, but we're building a new one on quantum mechanics. So kind of a range of things, both in the physics research and in the science for the public, the blending of science and art. And as I mentioned before, I'm also teaching a course this summer on my book at Columbia. Any Columbia students, or you don't even have to be a Columbia student. I do think they make you pay though. But if you want to interact with me on some of the big ideas of the origin of the universe and life and mind and galaxies and what it will be like in the far future, we'll be meeting twice a week, Tuesdays and Thursdays from 6 p.m. to 9 p.m. Eastern Standard Time as part of this course called Origins and Meaning at Columbia. Any of you guys want to go check that out? Love to have you in that class. Anyway, that gives you some flavor of the things that I'm working on in the moment. Asif asks, does the fabric of space-time really exist? Or is it an idea that Einstein used to visualize gravity? And if it does exist, what's it made of? Can it bend, and can space-time tear? And look, that's a deep question, Asif. I believe that Einstein thought that space-time was a real thing. People debate this, and philosophers have written, thousands of pages on the reality or not of space-time in the, say, Einsteinian sense. Here's where I come down on it. Space-time is enough of a something to define what we mean by accelerated motion. You see, if the universe was completely empty, no matter, nothing in there but space-time itself, according to the equations of general relativity, if you were to take two rocks, say, and have a rope between them and spin them around, according to the equations of general relativity, those rocks would pull taut, as you would think they would, based on your experience in the everyday world. But if there's nothing else in the universe, what are these rocks spinning with respect to? In fact, can you even define a notion of spinning if there aren't any benchmarks, physical benchmarks for motion? And according to the general theory of relativity, you can talk about the acceleration that these rocks are experiencing. What are they accelerating with respect to? Space-time itself. So space-time itself seems to be enough of a something to allow us to define accelerated motion. Now, given that, can space-time tear? And you're talking to somebody for whom the tearing of space-time is especially close to his heart. One of the insights that I was fortunate to be involved with is to show that within string theory, the fabric of space can rip. In fact, we did this in two stages. Our first insight was that space-time could rip in very mild ways that are called flop transitions. That's a technical mathematical term, however weird and colloquial it sounds. We then subsequently showed that far more drastic rips in the fabric of space, so-called conifold points or conifold transitions, were also allowed by string theory. So it's pretty much accepted that if string theory is correct, that there is a notion of the tearing of the fabric of space. And again, it's hard to imagine what one would mean by the tearing of the fabric of space if the fabric of space were not actually a real thing. So, in answer to your question, I would say yes, it is enough of a real thing to talk about acceleration, to talk about ripping. Okay, what else we got here? Any other questions, or should I? Well, I'm going to go for a few more minutes and then wrap it up. Okay, so Felis Super says, if you have two entangled particles far apart and you observe one of them, then can you still observe interference pattern in a double slit experiment on the other particle? And phew, it's hard for me to answer that question in full generality, but let me say it this way. So when you talk about the double slit experiment, the part of that experiment that really matters to this question is the ability of the superposed waves from the two different possibilities to blend and meld, to interfere and yield the bright, dark pattern. So the critical thing here is, can we retain that level of quantum weirdness even after a measurement? And the answer to that is largely no. When we measure a particle, the impact of that interaction is to get rid of all of the weird quantum possibilities, force them to ante up, is the language that I like to use, and decide on a single definite outcome. And when you have single definite outcomes, you're basically getting rid of the quantum weirdness. So in entanglement, you measure this particle and it causes this one to snap out of the haze. You're now in one of those single definite states. You have eliminated all of the quantum weirdness associated with superposition, the possibility that a particle could be in multiple states at the same time. And in that sense, you have gone away from the possibility of being able to expose superposition, expose quantum weirdness by virtue of your interaction, by virtue of that measurement. So the quick answer would be no. Pink Lady asks, oh, and Pink Lady apples. Those are my favorite apples, Pink Lady. Good. Did Einstein ever believe in a multiverse or a fourth dimension? Well, for multiverse, I don't think so. I don't really know precisely the history of the multiverse. Certainly, the quantum mechanical multiverse was introduced by Hugh Everett in 1957. Einstein died in 1955, so he probably didn't think about that at all. For the fourth dimension, that was an idea that emerged from Einstein's teacher, Hermann Minkowski, who you may recall was the teacher who thought Einstein wasn't going to achieve very much in his life. He said that Einstein was a lazy dog, and yet Einstein showed Hermann Minkowski to be wrong. But anyway, so when Hermann Minkowski learned about Einstein's insights into special relativity, he was the one who introduced this idea of time as a fourth dimension. Einstein resisted this idea at first. I think he felt it was too formal, too mathematical. Ultimately, though, he realized the power of thinking about space and time in a uniform language. And that uniform language is indeed the language of the fourth dimension that Minkowski introduced. So yes, Einstein definitely did believe in time as a fourth dimension. What else do we have here? Somebody asked why lecture 24 is not visible. I answered that earlier, so you can look back at the beginning, the very beginning of this live session. Let's see. Cambridge Breeze. Brian, what is your opinion on Stephen Wolfram's claim about his unified theory? I don't know. I think I addressed this a little bit in the last live session, but very briefly. Look, Steve is a brilliant person, huge impact on the world of science and mathematics with Mathematica. Anything that he says is worth thinking about, worth looking into. I haven't had time yet to do so. I do intend to try to get a better understanding of what he has in mind. My gut feeling is it's not the unified, it's not the answer to everything, simply because almost every proposal that's ever put forward is not the answer. So throwing it into that bin leads me to have skepticism when new ideas are proposing big revolutions in our thinking. But when it comes to Steve Wolfram, maybe it is a big revolution. So, all just to say, I need to look into it further before I can pass any sensible judgment on it whatsoever. And he's actually broadcasting the discussions that they're having in trying to push this program forward. I believe it's made publicly available. So if you want to listen in to people trying to develop Wolfram's idea, you can do that. And that's kind of very different, very cool, very exciting. So look it up online, and maybe you guys can report back next time on, if I haven't had a chance to look at it by then, if there's anything that you got excited about listening to that. All right, all right. What is your favorite sci-fi movie of all time? Maybe that's a good, nice, light question to finish up with. Although I have to tell you, part of me wonders how long we could go with this session. Would we all just sort of peter out, or would we like be able to go like 10 hours on this? I don't know. So what is my favorite sci-fi movie of all time? Well, I loved the original Planet of the Apes. You know, Charlton Heston on the sand, looking at the half sunken Statue of Liberty. Wow, that's spectacular. I loved Contact. I thought it just had a really good feel for the wonders of space and the wonders of time, and had a strong emotional component to it. I know that there are other sci-fi movies that I really loved, and I know that they're going to all come flooding to me. Maybe you guys can tell me your favorite movie in the chat right here, and as they scroll by, perhaps I can be reminded of the ones that really mattered to me. But those are the ones that come to mind. So Dan Cooper says 10 hours sounds good. All right, one person is happy to do that. Contact, Bohm Diaz like that film. Oh, 2001. Thank you, Eric W. Yeah, 2001, a great film. But I have to tell you, and you're going to perhaps consider me a Philistine for saying this, I tried to watch it a couple years ago with my kids. Maybe because my kids were there, that was part of it. But it was so incredibly slow in the beginning. Maybe we've all become accustomed to things having to move fast, and the velocity of the story, that it was really hard to hold my kids' attention. And I have to say, I began to wander a little bit too in the very beginning of 2001. Yeah, Interstellar, good film. And close to my heart too, because Interstellar, there's a beautiful scene in which characters go near the edge of a black hole. They spend time, their time slows down near the edge of a black hole, so they come back and everybody else has aged a lot. And as it turns out, that's actually the operative element in a story that I wrote back in 2008. And it was this one, Icarus at the Edge of Time, that I mentioned before about the boy going to a black hole. So that is the operative element in that particular story. So yeah, I think it's really cool when Einstein's general theory of relativity is brought into a narrative setting. Absolutely. Other Monty Python, yeah. So Meaning of Life, Part 1, love it. Yeah, can Run Lola Run. I like Run Lola Run. Somehow it didn't really stick with me as well. Oh, there it is. Barang, thank you. The Matrix. How could I leave out the Matrix? The Matrix speaks to all these issues about what consciousness is, the degree to which you can trust your conscious experiences, to what degree reality could be completely different from what you think it is based on your everyday experiences. So, in fact, in the course that I'm teaching, we watch The Matrix because even if you've seen it before, it just brings right to the fore these important philosophical issues about what science can ultimately tell us about the true nature of reality, because science is ultimately processed through the human brain. So everything that we know about the world is colored by our ability to think through and to experience reality. And therefore, there is this intermediary between us and the true nature of the world. And the Matrix shows you how that intermediary can yield a deeply misleading view on what reality actually is. Oh, yes. Abai Chaco, thank you. Inception. I loved Inception. I think Inception is, again, it's one of these films that plays with perception, plays with understanding, and look, how can you fault a film that uses a spinning top and perhaps the precession of the top to be used to distinguish between worlds that are real and worlds that are not? Yes, so some really great examples you guys give as the scroll is going by here. Paula asks, would you do a series on explaining the science in movies? I'd love it if you would do. And yeah, my friend Neil Tyson likes to take that particular arena on, and he does it with a wonderful degree of entertainment value. And so on occasion, I do weigh in on the science in movies, and I think, there could be a good series in there. In fact, we've been chit-chatting with some television producers, and that is one of the ideas that we have been kicking around just a little bit. The most important thing to bear in mind, though, is I think, when you watch a film, or at least let me speak personally, when I watch a film, I like to just let it wash over me. I love it when, if there is science, I don't need to think about the science. I don't need to evaluate it. I just like to be transported into a different world. When a film fails for me, where there's science in it, where either it's like so blatantly ridiculous that I just dismiss it, or if the film breaks its own inner rules. I don't mind bending the rules of physics, but don't bend them at will. Bend them, let me know the kind of rules that are going to govern the world that you're studying, and don't change it at the last minute, because I hate that, because that just feels laziness on the part of the writer or the director or the producer. So, but yes, I think that would be a fun, yes. DHHHHH says a beautiful mind. Yes, I love the beautiful mind. How wonderful to have an inner glimpse of the kinds of experiences that a brain can have if it's not working in the manner that's more familiar to us. It goes back to our question earlier on psychedelics and consciousness. Here's a case where it's not psychedelics per se, it's a brain whose functioning is somewhat different from the functioning of most of our brains, and that allowed that brain to have experiences that are spectacularly unfamiliar. And I thought that film did a wonderful job of giving us a sensation of what it was like to be inside that mind, and what it was like to be inside a mind that is at one and the same time troubled but also deeply insightful. So yeah, I think that is absolutely a beautiful example. Okay, is the speed of light, Muhammad asks, the limit in the multiverse? And how do I answer that question? I would say that the answer is yes, in the following sense. The multiverse theories that are really worth thinking about are the multiverses in which the distinct universes emerge from some underlying mathematical law. I mean, anybody can say, hey, what if there are other universes? And maybe those universes are filled with Swiss cheese, whatever. Anybody can do that. That's not interesting. What's interesting is when you have a mathematical theory that is motivated by understanding things in the world around you, and that mathematical theory then predicts the possibility of other universes. And in the mathematical theories that we study of that sort, the speed of light is an intrinsic quality of the mathematics, the general theory of relativity, the special theory of relativity, it's all in there. So in that sense, the qualities of light and its speed is not something that you change willy-nilly from universe to universe. It's something that's dictated by the underlying mathematics. Now, having said that, environmental differences in different universes can affect the kinds of speeds or kinds of qualities that inhabitants in those worlds would measure. So even in so there is a flexibility in that the environments can look quite different. The force of gravity can have radically different strengths. The qualities of electromagnetism can differ, and so for the electromagnetism is ultimately to do with light. So in that sense, there is a flexibility from universe to universe, but I don't want you to think that there is a things that are just changed at will. It emerges from some underlying fixed mathematical structure that can yield universes that have different environmental details, and those environmental details can affect the things that we measure. All right, guys, what do you think? Quickly tell me, do you want to ask a few more, or do you want to take a break until next time? I'll answer this question as you're answering them. So Ashant asks, if quantum mechanics makes the universe non-deterministic, then how are you going to figure out the grand unified theory? And I love that question because it's one that I get a lot, and it allows me to emphasize what quantum mechanics is not. Quantum mechanics is not a theory that somehow imbues the universe with some kind of deep indeterminism. The equations of quantum mechanics, which we studied in one of the episodes on Schrodinger's equation, those equations are deterministic. The math of quantum mechanics is just as deterministic as the math of classical mechanics. The only difference is, whereas the math of classical mechanics predicts definite outcomes for observation and experiment, the deterministic math of quantum mechanics only predicts the probabilities of getting one or another outcome, but it predicts those probabilities with deterministic mathematics. So quantum mechanics is deeply deterministic, but what it determines are possibilities as opposed to definite outcomes. And therefore, it's not like quantum mechanics makes everything uncertain or prevents you from making progress. Not at all. In fact, quantum mechanics yields the most precise predictions that we have ever had. We can make calculations with quantum mechanics and do experiments and find that they match to the 10th decimal place after the decimal point. You call that some kind of undeterminism or some kind of uncertainty? That's pretty damn certain. And that's really what quantum mechanics gives you. So you really need to avoid hearing the words Heisenberg uncertainty or quantum indeterminacy and employing them in a way that they are not meant to be used. And I hope that clarifies that very important point. All right. Danny Wong asks, why did the universe immediately collapse? I think Danny Wong means, why didn't the universe immediately collapse into a black hole following inflation? And this is an interesting question, because if a black hole is when you have a lot of matter in a region of space, and that region of space is affected and in some sense collapse in on itself, well, near the Big Bang, wasn't there a lot of matter? Why didn't the whole universe collapse in on itself? Two answers to that. Number one, the black hole solution of Einstein's general relativity assumes that the matter you're talking about is within a pre-existing spatial environment. When we talk about the Big Bang, there is no pre-existing spatial environment. The Big Bang creates the spatial environment, and therefore our intuition from black holes in ordinary space needs to be updated when we are trying to think about matter in a context like the Big Bang. Second, we believe that the early universe was very homogeneous, highly similar in distinct locations. And so it didn't create the centers, the gravitational centers around which matter would fall in to create black holes. So as inflation is happening, it propels everything outward. It propels space and time themselves to stretch. And in the aftermath of that, you have this nice, largely homogeneous realm in which things are moving outward. And so the homogeneity, which requires you not to have these gravitational centers, which will suck in the matter surrounding, as well as the outward swelling itself, counters the tendency for things to fall together into clumpy objects like black holes. There was an interesting one I just saw, and it just went by. Anand asks, what is your opinion about the Rig Veda? I can't give you an opinion on that. For that, you need to ask my brother. Maybe you got me confused with him. He is an expert on these particular texts, and he actually just taught a course on the Rig Veda, I believe, at Hofstra University in New York online. So look him up, ask him, tell him I sent you. All right. Someone just asked if I could say a few words about the many worlds interpretation of quantum mechanics. I don't know where that question went, but yeah, look, I just mentioned that the math of quantum mechanics is deterministic, but that it determines probabilities. So if the math determines that the probability of an electron to be here is 30%, and here to be 50%, and here to be 20%, the natural question is, when you undertake a measurement, why do you only find it at one place or another? What happens to the other possibilities that emerge from the mathematics of quantum mechanics? And the many worlds interpretation from Hugh Everett says, well, but here's what happens. If there are three possible locations for the location of the electron, and you measure its position, and you find it here, according to Hugh Everett, there are actually versions of you that find it here and here as well. Those possibilities do not go away, but rather they take place in a completely separate reality, a reality that in some sense the math of quantum mechanics separates off from the reality in which you found the electron here. So each of these possible outcomes is realized in its own separate world, and that's why it's called the many worlds interpretation of quantum mechanics. So it's a highly controversial subject. My friend Sean Carroll recently wrote a book. He is a dedicated many worlder, if you will. I am not as dedicated to this approach. I think there are mathematical details that still need to be ironed out before we can take this idea seriously. But yeah, it is one viable approach to trying to make sense of the reality which the quantum mathematics is leading us to. Not everybody does. So Eric W says, shout out to the eels, and that's right. So Hugh Everett's son, I forgot his first name. Oh, darn. Maybe Eric, you can tell me. But Hugh Everett's son formed a group called the Eels, and in fact, participated in a very interesting film that I can't remember the name of the film. God, I'm becoming forgetful in my old age here. And it's a very interesting film in which Hugh Everett's son was reflecting on his father and his father's role, at least in part, on developing this many worlds approach to quantum mechanics. Let's see what else we have here. Naveen asks about my opinion on white holes, and white holes are basically time reversed versions of black holes. So since the laws of physics are time reversal invariant, if they allow black holes to form, you'd assume that white holes, where not everything's falling in, but everything's spewing out, would be allowed to. Many people think that there are principles that forbid the creation of white holes. I am of the opinion that white holes likely do not exist, but I should say that there are people who think about these ideas and have different opinions and have thought about it more than I have. So I can't really give you a definitive answer on white holes, but no, I do not think that white holes are real. Someone asks, and it went by. William Selby asks, what are your thoughts on loop quantum gravity? And look, William, my view is that I'm glad that there are people developing alternative approaches to blending quantum mechanics and general relativity. It's a very important subject. We have been struggling to realize the dream of a unified theory that would put together the laws of the big and the laws of the small into one coherent mathematical framework. And to put all your eggs into one theoretical basket, namely that of string theory, would not be a good strategy for the species, right? So I'm glad that there are other approaches to quantum gravity that are being developed. I think that string theory has the better chance of being the right theory for many reasons. the mathematical structure of the theory feels more convincing to me. The way it deals with quantum mechanics feels more convincing to me. And a variety of other technical details that maybe I'll spell out in one of these Your Daily Equation episodes. Yeah, maybe I should do one on loop quantum gravity. Like I said in one of the earlier episodes, so many equations, so little time. I don't know what I'll get to. But, you know, so my thought about loop quantum gravity, it could be the right theory. I'm glad people are developing it. Maybe we'll find connections between it and string theory before all the dust is settled. So I'm a proponent of the varieties of approaches that we take to solve deep challenges, and loop quantum gravity is an absolutely viable approach, and I'm glad that people are working on it. I don't think, however, that it's the right approach, or I'd be working on that myself. Okay, man, what do it's still rolling along here. Okay, what else? How does it, Prayag, how does it feel to be vegan? I don't know. I think I've been weak ever since I turned vegan 25 years ago. So I'm not sure. I don't know how to answer that question. Dr. Brian from Muhammad, how is it sufficient for just one difference between matter and antimatter to create everything? That's referring to a little video that we had, a quick Your Daily Equation, where I noted that if you had 1,000,000,001 particles of let's call it of matter, 1,000,001 particles of matter for every billion particles of antimatter, then when the matter and antimatter find each other and collide, one particle of matter would be left over. The question is, how is that enough? Well, it's enough to create all the stuff in the universe, which is not just one particle. Well, when you look at the cosmological evolution of matter from just after the Big Bang until today, you can calculate how much stuff would be, say, in our observable universe. And the amount of stuff that you need in order to have the stars and galaxies ultimately form is such that you only need about 1 part in a billion of all of the matter particles that could have been created. So I wasn't trying to say there's only one particle left, because the universe has much more than 1,000,000,001 particles of matter and much more than 1,000,000,000 particles of antimatter. But I'm saying if that level of imbalance persists throughout all of space and applies to all of the gargantuan numbers of particles of matter and antimatter that are across all the observable universe, then the amount of matter left over when the matter and antimatter collide and annihilate would be enough to yield the stars and galaxies. What else? All right. Already asked, would you rather time travel to the past or to the future if you could only take a one-way journey? Already, my view on that is quite straightforward. I would absolutely prefer to travel to the future, which is a good thing because time travel to the future is within the laws of physics and time travel to the past is likely not. But why would I rather travel to the future? When I get to the future, I can read about the past. I can see videos about the past. I can, whatever, put on neural implants that will allow me to learn about what happened in the past. The future is the big mystery. The future is the one that we seem not to be able to learn about in detail by sitting here at this present moment. And therefore, the future holds much more of an allure to me than the past. Having said that, as a human being, I'm not going to the future if I can't take the people that make life worth living. I'm not going if my wife says no. I'm not going if my kids say no. Maybe there are a few others I throw into that group, so I don't mean to exclude anybody. But yeah, in terms of the distinction between past and future, to me, it is the future that holds the greatest attraction, not the past. Can I explain? Abai asked about the delayed choice quantum eraser. And I can. I'm actually going to refer you, I don't do this often, but I'm going to refer you to my book, Fabric of the Cosmos, Chapter 7. I'm sure you can get a bootleg PDF version online. I'm not asking you to buy it. And there I go through great detail on the question that you addressed. So I'm going to leave it at that because it would take me pretty far afield to even set up how that experiment. Nomad asks, is there a Heisenberg principle for thought processes? And look, this is similar to a question from before. Does the uncertainty principle apply to thought processes? Yes, it does. Does it apply to blue cheese and Swiss cheese? It does, because all those things are made up of particles. Is there something special about the Heisenberg uncertainty principle as applied to human thought, as applied to Swiss cheese or blue cheese? I don't think so. Now, could I be wrong about that? Could quantum mechanics be more tightly connected with conscious processes? People have suggested that. Serious people have suggested that. Eugene Wigner, one of the great minds of the last centuries, suggested that, at least for one period of time. I don't feel that way. I don't think mind is special in the sense of having any other qualities beyond particles and physical law governing those particles. And that's exactly how I would describe cheese. What is special about the mind is that the particles are highly arranged, having emerged from eons and eons of evolutionary processes. That's what's special about the mind. Not that it deals with quantum mechanics in some different way, but rather that it's highly organized. The pattern of the particles is just exquisite compared to the pattern of particles that make up a chunk of cheese. So in that sense, yes, Heisenberg's uncertainty principle matters, but no, it doesn't play any special role. And that really is the key thing to keep in mind. Okay, so Gabor asked, does Bohmian mechanics have any problems in replicating entanglement? And it does not. And in fact, Bohmian mechanics is, in some sense, an antidote to the weirdness of entanglement as described in the more conventional quantum mechanical approach, the Copenhagen approach, say. Copenhagen approach, entanglement, totally weird, because particles really are in a mixture of, say, up and down at the same time. So how in the world could measuring a particle over here cause this particle to snap out of the up and down? That's the spookiness. That's the craziness. Bohmian mechanics comes in and says, there's a very simple explanation. This particle, when you measured it and found up, it was always up. This particle, when you measured it and found it down, it was always down. Nothing snapped out of a fuzzy haze, because there is no fuzzy haze in Bohmian mechanics. In Bohmian mechanics, the probabilistic nature emerges from a different source. It emerges from your inability to understand the true qualities of a particle. But the particle itself does have the qualities that measurement reveals. Measurement doesn't cause those properties to emerge. Measurement simply reveals the pre-existing properties that the particles have. So from that point of view, there is absolutely nothing strange about entanglement in Bohmian mechanics. All right, so what do we do? Should we wrap this up here? EPR paradox. Azan, you can find that in one of the earlier episodes. I want to answer one good question and then be done for today. I keep saying that. I think I said that 2 hours ago. What form of matter, Akash asked, what form of matter does a black hole consist of? And look, in the traditional description, Akash Shalar, of a black hole, matter falls into a black hole. It gets infinitely squeezed. What does that really mean? Infinitely squeezed at the center. And there isn't really much happening between, say, the center and the event horizon of a black hole that's, say, been hanging around for a long time. So in that sense, a black hole kind of consists of this singularity, which, as I said earlier, means we don't know what's going on at the center, empty space, event horizon, which itself is empty space, but it does have a very important implication that anything that falls over the edge can't come out. That's the traditional classical description. Quantum mechanically, this story is more involved. People envision that maybe the edge of a black hole is a firewall, a place of increasingly high temperature. Anything that falls in gets incinerated at the edge. Maybe there isn't even an inside beyond the firewall. My friend Samir Mather, maybe you guys know him, as I think there are a few folks from India that are following our discussion here. Samir Mather is at Ohio State, a brilliant Indian physicist. I shared an office with him back in the 1980s, and he came up with an idea that black holes may actually really be, in some sense, made of strings that are entangled with each other in what he likes to call a fuzzball. And so a black hole might actually be a fuzzball, which would mean a black hole is not that different from a star. A star, you got this structure that burns on the outside. A fuzzball could be a structure that burns on the outside too. It just is an extreme version of that. So we don't really fully know the quantum mechanical answer to the question of the deep constituents of a black hole. So Bohm Diaz says, I'm in Columbus, Ohio. Fantastic. You should go look up Samir. Tell him I said hi. Tracy Day asks, what are we having for dinner? Tracy Day is my wife, who has entered the conversation with a very, very deep question, which I suggest she means I should probably wrap this up. So Tracy Day, wife, I think we'll have tofu, black bean sauce, but I'm going to answer one more question that just really, wait, could this be it? No, it's not. Wait, I like this one. So John Faulkner asks about entanglement. I'd love to answer that, but I've done so much on entanglement, John, that I'm going to do the rude thing and refer you to your daily equation episode on entanglement, which you can easily find. What else? Give me that one question I'm looking for. Come on, there must be one here. Good. Someone's now talking to my wife, Tracy. That's nice. I appreciate that. So I'm going to end with my friend Ludwig von Beethoven, a great supporter of the series, who asks, how is the proposal that time might be just an illusion compatible with the theory of relativity? And you're right, Ludwig von Beethoven. There are people who say that time is an illusion. And well, two answers. So there is a long history of work that's been done on trying to argue that the right way to formulate physics, and even the right way to formulate the general theory of relativity, it's all about relationships, as opposed to there being this drumbeat of time. Even if that drumbeat is different for us depending upon our motion and the gravity we experience, that the real fundamental right way to formulate relativity would not have time in those basic equations. The time itself would simply emerge from those basic equations. And there's some evidence for that in string theory too. So I'm not suggesting that this is the right way of doing physics or the wrong way of doing physics. I'm merely noting that there's a long history of people developing that idea. And the reason I raise that is because you can have time emerge, a la these approaches, such that it has the qualities that we experience in everyday life, and it has the experience that Einstein revealed through special and the general theory of relativity. It could be that time is a quality that is only relevant on, say, certain length scales or certain duration scales or in certain environments, and that fundamentally there is no time written into the deeper laws that we've yet to fully discover. That wouldn't mean that time is an illusion. That would mean that time is emergent. And so I think that that's the way that most of us think about this possibility of there not being any notion of time in the true fundamental equations. At that level, I guess time would be illusory, because in those basic equations, you wouldn't see any conception of time. But certainly, time as we experience it is real. We all experience it. Time as Einstein articulated in relativity would be real too. It just wouldn't be as fundamental. So there's a difference between something being illusory and a mistake and shouldn't be spoken of, and something being illusory in the sense that it's not fundamental, that it's emergent. So I think emergent would be the better language for discussing that notion of time. All right, so I think that's more or less it for today. You should join us on Monday for the next episode of your daily equation. Again, some of you asked where episode 24 is, and we'll get it out maybe this weekend or maybe on Monday. As I noted early on in the session, I made a small mistake, a small mathematical mistake in that episode. I want to fix it. So we're just going to fix that and we'll get it out to you. Nothing conceptual. It's just a technical thing. I wrote an extra derivative in one equation. So yeah, I'm being perhaps a little bit too persnickety to ensure that that is done right, but I'm going to do that right. And then on Monday or Tuesday, we'll pass into Einstein's ideas of general relativity. We did special relativity. And we'll talk about curvature and gravity of space-time curvature. And maybe we'll do some things on black holes. That would be quite natural. I'll turn to cosmology. I want to give you an understanding of the Big Bang and inflationary cosmology. And who knows where we're going to go from there, if at all. Maybe that will be a natural winding down time for this series. But, you know, if you keep watching and keep talking and keep asking, I'm going to still be here. So who knows? Maybe we'll keep on going a little bit further into the summer than I initially anticipated. You know, life issues can sometimes get in the way of that. But I'm willing to keep an open mind and listen to what you guys would enjoy doing. All right. Again, if you don't follow me on Twitter, please do. In fact, sometimes when I'm not doing an episode of your daily equation, I wish I could just send out a tweet and reach you guys because I kind of feel bad. So if more of you would follow me, it would be an easier way for me to be in touch with you guys. World Science Festival, you should subscribe. I think there is a subscribe button somewhere in this down there. And a lot of great content that's already on the World Science Festival website. Final announcement before I go. World Science U, the educational arm of the World Science Festival, we are relaunching really soon with a lot of really interesting online courses that are all free. I have a full special relativity course there, both with math and without math. We have courses that go from cosmology all the way to issues of consciousness. So all for free. You should definitely check that out. It'll be available, I think very soon. I think April. No, we're in May already. So maybe it's in the next week or two. So keep your eyes out for that. All right, guys. Thank you. I've enjoyed this session with you, and looking forward to picking it up live next Friday. But we'll have our usual doses of your daily equation coming up this week. All right. Until then, this is Brian Greene signing off.